willing to just stay where you are for the next few weeks so that I can learn your names. I'll learn them by where you are first, then I'll start to recognize your face, then I'll put names and faces together. I just want to say a couple quick things about technology. And so first of all, if you've looked at my Canvas site, you may have seen that the next week is up. So this is how I organize it, where the previous weeks will be chronological in the bottom part. The current week will be at the top. And now there's a new module called Resources. This is where, if you would like to watch any of the videos that we make, you'll be able to spot those. I have, it's just a YouTube channel, but I organize it by class. So here's us. Anything you want to see will ultimately get posted there. And if you need any help navigating the YouTube site, let me know. I'm happy to help you. I don't want it to be anything that's a struggle. Couple other things you already know, but I know that some of you are going to need reminders that your phones should be completely out of the way. They should be your backpack, they should be purse, locker, the pouch. I can find a spot in the classroom to keep them, including locking cabinets and drawers if you're more comfortable with that. I am not going to be a jerk about it, but there will be a point at which I need to follow the expectation, which is if you have your phone out, I'm going to take it. It's not going to happen probably today or even realistically tomorrow. But you should expect by the end of the week, when I see you on Thursday, you should be used to the idea that you just don't get your phones out. So be aware of that. Chromebooks, a couple of things. First of all, I've said this a couple of times, but I want to reinforce. I don't want you using personal devices in the class. So if you have a laptop that you just love, you can bring it, but I'm going to ask you to use your school-issued Chromebook. If you don't have one, go get one. If you have one, but you forgot it, I have loaners. If you have one and it's not charged up, I have one charging cable. And if we run out of charging cables, which we will, then you can use one of the loaners. So if you really don't want to use one of my loaners, bring your Chromebook, make sure it's charged, and for good measure, bring a charging cable, just in case. The other thing about Chromebooks is a lot of you are in the habit, which is it's not a bad one, of walking into the room, getting your Chromebook out, and opening it up. And what I'm going to say is just in general, they should be closed until I tell you to open them. I know some of you like to take notes on your Chromebook, or you like to follow along on your Chromebook, and here's the thing. No, don't do it. I'm going to ask you to, not today, but in general, there are going to be times when I ask you to write stuff down. And that means write it down, pencil and paper. If you have an agreement with another staff member whose authority supersedes mine, which there's many of, then we'll talk about it separately. For some of you, I will provide notes because that's what the ask is going to be. For others of you, it'll be really clear that you are allowed to use your Chromebook. Otherwise, close them, keep them closed. I'll tell you when to open them, and then when we're done using them, I want you to close them again. So at this point, everybody should close them. And then the other two, let's see, I told you about videos already, so the other thing I wanted to mention is turning stuff in, and I'm going to be, there's going to be an adjustment, and so you don't have to worry about it, but in general, the way it's going to work, and I'll talk you through this a few times, the way it's going to work is I'm going to determine whether something is turned in and when it was turned in by looking at Canvas. So if you're not turning stuff in on Canvas, then it's not in. That means anytime there's handwritten work, you got to take a picture of it and turn it in on Canvas. And you'll have time in class to do that. You'll need to use your Chromebook, which means the pictures are going to be blurry, which means if there's handwritten work after you've taken the picture, I also want the handwritten work. And I know it's a pain. And if you would like a more detailed explanation of why I'm doing this, I'm happy to talk to you about it, but let's do it not during class. You can come by and I'll explain it to you. I think it'll make sense. I'm not doing it to be difficult. It actually is going to play out, even though it's a extra step one way or the other for everybody, it's gonna play out well for all of you to do this. So you turn in handwritten work, both as a picture on canvas and on paper every time. Yeah?
Could we just like write a text box saying
Nope.
it's done? And then
Nope, close it. Will you close your Chromebooks? Nope. I'm gonna ask you to take a picture, and I'm gonna ask you to turn it in by hand. We can talk about the reasons if you want, but that's how it's gonna be. Okay, let's see. So I'll remind you again tomorrow when I see you, but and you all haven't turned anything in yet. You will on Thursday, but basically what's gonna happen is some of you are gonna do one and not the other. And so what I wanna make sure is you understand two things. Number one, I'm gonna be flexible for the first couple of assignments, so you don't have to panic while you're getting used to the plan. Two, if you do one of those things but not the other, then your work won't get scored. So just know that, and again, there won't be a penalty for the first couple of weeks while you're figuring it out. But then after that, I'll explain what's gonna happen. So lock yourself into the idea that handwritten work gets turned in, quick picture, and also give me the paper. And let's see, so we've got a couple of things to do today. I wanna just show you something real quick that I think it's worth thinking about. It's kind of interesting, and it is not gonna be universally applicable, but my guess is all of you at some point are gonna struggle with something along these lines. So we're gonna shift gears, talk a little bit about motion graphs. Before I do that, does anybody have any questions about technology, Chromebooks, phones, about turning things in, about access to the videos? Okay, excellent. So let me just show you something, and it's really kind of an interesting thing to think about. We are all accustomed to using maps. Some of you still use paper maps like I do, but almost all of us have used Google Maps, right? So if we use Google Maps, and we're gonna talk about like getting from Fred Meyer out to CV, what happens is that there's a bunch of different ways to go. One way you could go is you could go down Kings all the way to Walnut, and then you could go out on Walnut, and then you could go up Highland, and then go out to CV and park in the parking lot, right? And when you look at the line that this makes, this is a spatial representation of your path, the path that you traveled to get from point A to point B. And that is super intuitive to all of us. We are looking at these motion graphs, and the motion graphs that we're looking at look a little bit different. If we look at a position versus time graph, and it's an all day, so I'm not gonna go into the nitty gritty about this today, but I will on tomorrow when we have a little bit more time. X is the variable in physics that we use for position. T is the variable that we use for time. So this is a position versus time graph. If we were to look at a typical position versus time graph, like a realistic one, the ones that you were creating the other day with the motion sensors, they look something like this, you know, so I just made that up, but that's a reasonable approximation of what you saw the other day, right? Did everybody see something look like this? Did yours look different?
Ours looked like,
Jaggy. Yeah, yours had what we call noise. That wasn't good data. Were you really moving like that? Were you really moving back and forth incredibly fast?
for one of them,
What's that?
for one of them.
Like how fast? Like 30 meters per second? 40?
Yeah, about there.
Okay, 30 meters per second is like a third of a football field
Yeah.
in 1 second.
Mhm.
Is that how fast you were moving?
I'd say so.
I don't think so. Yeah, I don't think anybody in here can move that fast. Not me. Nope. I can pretend, but I can't really do it. If you get good data with a position versus time graph on our sensor equipment, it's gonna look like this. It's gonna be smooth, nice smooth curves. Any of those jaggies mean it is not really tracking one object. You get jaggies when it picks up on something that's close, and then it picks on something else that's far. The sensor has no idea what the sound is bouncing off of. All it knows is sound bounced back quick, and then the sound bounced back in a longer time. And so, if it were one object, it must have moved, and it must have moved really far in a very short amount of time. Therefore, it must be moving really quickly, but that's not reality. So, this is what your graphs will look like if you get all the equipment set up right. So, this is gonna be one of our goals. But one of the interesting things about this is, if you think about this as a two-dimensional map, like the map that I just drew showing Fred Meyer and CV, then it looks like you start here and you walk this way, and then you kind of turn this way and you walk this way for a while, and then you kind of turn this way and you walk this way, and then you turn again and you walk this way, and then you walk this way. And when it's all said and done, what it looks like is you started here at this location on a map, and you ended up walking to here. But this is not a map. This is a position versus time graph. This isn't two-dimensional, it's one-dimensional motion. Our sensors can only tell you how far something is away from the sensor. If you move side to side, or up and down for that matter, it doesn't know what to do with that information. Which means this is not an object that's moving from here to here. The correct way to read these graphs is to take your finger and look at two things. You can kind of you could even use a ruler, you could use like a straight object to kind of evaluate this. The first is, where are you? That's the y-axis. The second is, at what time were you there? That's the x-axis. So, if we looked at the scale on here, and I'm just gonna make this up, this is not what would show up on our motion sensors, but let's just pretend that it goes out to like 8 meters, and let's suppose that it does this over the course of 10 seconds or so. What's really going on is you're 3 meters away from the sensor when you started collecting data. You're still 3 meters away from the sensor after 1 second. You're still 3 meters away after 2 seconds. This line right here represents no motion at all. You're not moving. From 0 seconds to 2 seconds, you stay at the same position relative to the sensor. And then, from 3 seconds to 6 seconds, you start moving. You're 4 meters away, you're 5 meters away. At about 4 seconds, you're 5 meters away. You're 6 meters away at about 5 seconds. You're 6.5 meters away at about 6 seconds. And then you start moving back. You're about 6 meters away again at 8 seconds. And then you start moving away from the sensor again. If you looked at this, you're maybe 6.5 meters away again at about 10 seconds. This isn't super intuitive. For some of you, it wasn't difficult, but it isn't intuitive. When our brains see a line on a graph like this, and we are told this represents your position, our brains say, oh, we started here and then we went here. We think about it like we would see a little figure on a map, like a video game, like leaving a little trail behind it. I started here and I went to here. But this 2 second period, the way that I've drawn it, represents no motion at all. That is not super intuitive. So we're gonna have to get used to that. And we're gonna have to get used to even more, because it gets more complicated when we start thinking about, you can do this, when we start thinking about velocity versus time graphs. Because velocity versus time graphs, while it's still depicting one-dimensional motion, it's not telling you where you are at all. But instead, it's telling you how fast you're moving and in what direction. So if this is a velocity versus time graph, if we had a graph that looked something like this, and we're not going to have any graphs that look perfectly like this, but we can kind of pretend. Now, we can't say at all, well, you started here and you went to here and then you went to here and then you went to here. There's nothing on this graph directly that tells us where you are. The proper way to read this kind of a graph is the same way we read the position versus time graph, which means kind of take your finger and you look at the two things at once. One is, where are you on the y-axis? And the other is, where are you on the time axis? So when data collection started, this was your speed. If this is in meters per second, like our sensors are, then this shows motion of 2 meters per second at the time that data collection started. You're still going 2 meters per second at this time. Maybe this is 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5, 6, 7. So you're going 2 meters per second after 1 second. You're going 2 meters per second after 2 seconds. And then at 2 seconds, you're not moving at all. You have no velocity. 3 seconds, no velocity. At 4 seconds, you have no velocity, and then you start moving -1. We talked a little bit about this. That's just direction. This means toward the sensor. So now you're moving at 1 meter per second toward the sensor, and you're still moving 1 meter per second toward the sensor after 5 seconds of data collection. You're still moving at 1 meter per second toward the sensor after 6 seconds of data collection. Reading these graphs takes a little bit of practice. What you're going to find is, in general, you are going to look at something like this, and you're going to want to say, well, you start here and you go to here, and then you go to here, and then you go to here, and then you go to here. But on a velocity versus time graph, there isn't any position information. It's just telling you how fast you're going. So what I'm going to ask you to do today is start, and we'll finish this tomorrow. And this is not a quiz. It's not even an assignment. It's just something to think about. What I want you to recognize, though, is this represents what I'm going to be asking you to do in about 10 days. You're going to need to be able to do something like this. So I call it the Motion Sensor Challenge. You can think of it as like a preview of what a quiz in this class might look like for this material. So what I did is I actually made a graph using our sensors of me walking. This is a velocity versus time graph. And what I want you to be able to do is tell me exactly how you would move to reproduce this graph. Then I want you to actually do it and see how close your movement matches up with this graph that I made. What does this motion look like? Ultimately, we're going to be connecting 3 things. 1, actual motion that you can look at and describe. Oh, you're walking this way, you slow down, you stop, then you keep walking in the same direction, you speed up, and you just go faster and faster and faster. The second thing you're going to match that up with is a graph. What does that look like on a position versus time graph? What does it look like on a velocity versus time graph? And we'll look at a different kind of graph too, an acceleration versus time graph. And then the third thing we're going to match that up with ultimately are some mathematical equations for position and velocity and acceleration. We won't get there this week, but we'll start looking at those at the end of next week. So what I want you to do is to work with, just work on your own at first. Ultimately, you're going to test this, but you won't do that until tomorrow. And when you test it, you'll need to work with some other people just because of equipment limitations. But I want you to see how close you can come to describing exactly how you would move to recreate this graph. Now our class gets out at 9:55, and in between now and 9:55, I want you all to do 2 things. 1, I want you to write a description of this. The assignment's on Canvas, so I'll leave this picture up